Welcome, dear viewers. This is the second lecture for mathematical foundations for machine learning. As I told you, as you know, in our first lecture, we discussed what vectors or matrices or scalars or tensors are, and then we also discussed how a directed line segment is a vector, because a directed line segment in a plane is actually it actually is equivalent to a pair of numbers, and if the vector is in space, then it is equal to this a triplet of numbers. Now, so on and so forth. Now we will, as I promised you, now in this video is about dot product of two vectors. What does that mean? Dot product of two vectors. As we saw, as we saw in our previous this video, we saw that we can think of a directed line segment as a vector. This is a vector. Then you can also think of this as a vector. A and B. Suppose I name them A and B. These are two vectors. They have some angle between them. Now, you have heard of parallel lines. Two lines are said to be parallel if they are like this, and if they are not like this, they are not said to be parallel. They have parallelism here, but here, suppose for example, here they don't have a parallelism. But in case of vectors, there is a slight difference. And what that difference is? As you know, first, let me remind you that if you have a vector, a line, directed line segment on the screen, in the plane of the screen, this is a vector A in the plane of the screen. Okay, we know that it has two components. One component, horizontal component along x-axis, the other component, vertical component along y-axis. We also saw that these two are perpendicular. These two components of the vector are perpendicular. X component and y component. X and y are perpendicular. That is expected. X and y are perpendicular. So are x and z. X, y, and z. So we have this situation here. Now you have this directed line segment, and then you have this, and you have this. These two directed lines. These two components. Since a vector can have two components, and you can see the two components of this vector. Suppose the same vector is now oriented like this. This A is now oriented like this. What is the difference here and difference here? In this case, the vector A is not tilted, is not inclined so much with the horizontal direction as it is. That means it is the angle that it makes here is more than what it makes here. It is towards vertical. It is more vertical. This A is more vertical. This A is less vertical. Now, because of this increase in its verticality, we have its x component now. Its x component will be here from this point to this point, x component. Then y component will be this. How do I know this is the x component? Why not this x component? Because if I go from this point to this point and then turn and travel, I will never reach this point. You have to reach this point, and for that matter, you have to look how you have to travel. Okay, now how much you have to travel? So this is the x component, this is the y component. If you can compare this x component and this x component, one thing you immediately notice is that this x component is longer than this x component. This vector has a bigger x component as compared to this vector. Suppose now we make it more vertical. This is A, and now we make it even more vertical. So it is like this. This is A, this is B. Now what is the x component of A? X component of A is this. and then this y component. What happens to x component of a? It decreases further. It even decreases below this. What do we observe then? We observe then that as the angle, this angle which the given vector makes with the horizontal direction, x-axis, as this angle increase and increases, x component of the vector decrease and decrease and decrease. And if the angle becomes 90 degree, something like this, if it becomes 90 degree here, this is a, this is b, and now the angle becomes 90 degree. When angle becomes 90 degree, none of its component is parallel to AB. That is, none of this its component is in horizontal direction. You can see it easily. Another way, another way of visualizing this is that, suppose you have a building, like say there's a building like this wall of the building, and then you support a, suppose you have a ladder that you support with the building. This is during daytime. What happens there is that a shadow of this ladder will be cast on this. There will appear a shadow of this ladder. This shadow is its x component. If you now tilt it more, if you now actually make it more vertical like this now, what will happen to the shadow? Oh, it will be same. I'm sorry, because the length of the ladder, of course the ladder now will not reach this is a wrong example. Ladder will not reach now the wall. It is better to say like this. Then when you suppose you shine light from the vertical direction onto this vector, then this vector will form a shadow on this. That shadow will be exactly from this point to this point. Why not here? Why shadow will not be here? Because at this point light will fall. There is nothing to stop the light from falling at this point. On the other hand, there is something that stops the light from falling at this point. Similarly, there is something that stops the light from falling on this point. Similarly, stops the light from falling on this point, and so on. So, what will be the length of the shadow? Length of shadow will be this much. Exactly this. Exactly this. Now, when the same light is now shown on this, you let the light fall on this like this. Now, what about the shadow of this? Shadow will be much smaller. And when the light is allowed to fall on this, what will the size of shadow here? Size of shadow will be simply this. There will be no shadow in this region because light will directly fall on that. So this x component, one can think of it as the shadow. Okay, now if you now let light fall on this, okay, and if you realize that a straight line does not have any thickness, it is not thick, it is of negligible thickness, then light, this will not cast any shadow at all. There will be no shadow on B. So we say that this does not have an x component. It does not have an x component. Okay, I once again tell you that this does not have an x component. This does not have an x component. No component in this direction. On the other hand, this does have some, that is this, from this point to this point. How can you understand this? You imagine that light falls on these two simultaneously. The light falling on this will form a shadow here, but light falling on this will form no shadow. There will be shadow only at the bottom point of this. That shadow will not be visible because that shadow is actually that shadow is so small that it provided, but it will be very small provided if you think of the line. But if you think of the ladder, then it may not be small. A line does not have, by definition, line does not have a thickness. Now you will ask, if it does not have a thickness, why should we show it like a something thick like this? Even this has thickness, sir. Even this, that is something forced upon us, because if we don't include at least a little thickness, then we won't be able to show the line at all. So I hope that you understand this thing. Now come to the point. What is that? You have two vectors like this, A and B, or two vectors like this. Next, you have two vectors like this, like this. Look at the difference. Now you have two vectors like this. Look at the difference. Now lastly, you have two vectors like this. This is B, this is A. Okay. Are these, my question is, are these parallel? Yes, sir. They are parallel. Certainly they are parallel. Are these parallel? No, sir. On the face of it, they are not parallel. But with vectors, it's a different story. Had these been two lines, then your answer would have been correct. But since these are two vectors, you will have to modify your answer. Why? Because see, this A, make this A separately here. What you have learned in your previous video lecture, you learned that A has two components, one along this, another along this. These are its two components. This A will have two components, one along this, this is one component, this is another component. This component, this horizontal component of A, is parallel to B. Even though full A is not parallel to B, but a part of A is parallel to B. But so we say that even here there is a parallelism, there is some amount of parallelism between these two. But the parallelism here is less than parallelism here. Why? Because here in this case, whole of A is parallel to B. And in this case, only part of A is parallel to B. Now this part which is parallel to B, this goes on decreasing here. This decrease here. See, again, find this x component, that is this. Find this y component, that is this. Look, compare this x component with this x component. It has shortened a lot. This means parallelism between these two decreases further. And parallelism between these two. Now, how much is the parallelism between these two? Nothing. Zero. There is no component of A in this direction. Having no component in this direction can be explained by physics as well, better by physics. In fact, the fact is that if you want to understand mathematics, the best way which I have found, that is through physics. Physics gives mathematics its meaning. It infuses life into dead symbols of mathematics. What is the example? Example is this. Suppose you have a box. This box, some sort of a box, or suppose you have a box with wheels like this, in order to minimize friction. And this box has a hook here, and with the hook you tie a rope, a string, and hold that rope in your hand. You hold this rope in your hand. Okay, this is your hand, and then you pull on the rope this way. When you pull on the rope this way, the box will move horizontally. It will move only in this direction. It will neither go up nor fall down. It will simply move horizontally. But now imagine this case for the box. Now suppose you tie this rope not here, somewhere here on the top, and then hold the other end of the rope in your hand, and then pull with your hand. You pull it vertically. Now what will happen to the box? Since you are pulling upward, the box will be lifted in the upward direction. It will move in the upward direction. When the box moves in the upward direction, it does not move in the horizontal direction. It neither goes there nor goes there. It simply moves up. Here, the box moves in the horizontal direction. It neither goes up nor goes down. We say that this force is purely horizontal, purely x force, purely horizontal force. We denote it by x. This is along the x-axis. This force is purely horizontal. This means that it produces a motion, which is directed in the horizontal direction. What about this force? This force is said to be pure vertical force. It produces a motion that is directed vertically up. Okay. Now, we say that this force does not have any part, any component in this direction. By the way, a component means part. This does not have any part or in this direction, in horizontal direction. Now see, suppose we change the situation to a third case. In this third case, suppose you tie this rope here. You tie a hook here first, and then the rope, and you are pulling it like this, like this. It is as if you are walking by, and this is road. This road. You are walking and pulling at this, and this is you are here. You are here. Let me show you. You are here, something like this, and then you are walking in this direction and at the same time pulling it. Okay, when you pull this box, now the box will not move like this. The box will be lifted up. It will go here, provided the box is not too heavy. It should be light. Now the box moves up. What is the motion of the box now? The motion of the box is now two types simultaneously. The box moves horizontally as well as rises vertically. This box now is doing two things, two jobs at the same time. It is moving horizontally as well as moving upward. We say that this force is not a pure force. What does that mean? It means that this force produces both a horizontal effect and a vertical effect. How does it produce horizontal effect? Because the box is now here. This means that box has been horizontally displaced. Horizontally, it has come here, and box is not only displaced horizontally, it is also displaced vertically. So box is upward. So this force has two components, Fx and Fy. Fx and Fy. This is the story of components. So when the force, suppose this force had been like this, then this force, this vertical force, does not have any horizontal component. In this case, the box will move only upward. It will not move horizontally here, horizontally there. Similarly, if a force is horizontal, it does not have a vertical component. The box will not go up, or box will not go down. So what we have seen then, these components, see, this vector A will have no component now in this direction, in the direction of B. Here it is fully parallel to B. Here it is partially parallel to B. Here it is less parallel to B as compared to this. Here it is not parallel to B. Very good. Now this parallelism between two vectors is measured by dot product of two vectors. We say dot product of two vectors, and it simply means parallelism between two vectors. That means dot product is equal to, it measures, dot product measures what? Measures parallelism of two vectors, parallelism of two vectors. Or we can also say it measures alignment of two vectors. You call it parallelism or you call it alignment, it's one and the same thing. Okay, now dot product is parallelism. What is dot product here? When I ask you what is dot product of these two vectors, you should immediately recall that sir said that dot product means how much they are parallel, how much parallelism is there. You can say, well, sir, parallelism, I don't know how much it is, but I know it is maximum. So parallelism maximum here. And in this case, we say parallelism is equal to A into B. We say A into B simply. A into B. Parallelism dot product in this case is same thing as the normal product. Suppose you have to multiply 3 and 4. How do you do that? You say 3 into 4. Dot product is like this product of two numbers. if the vectors are parallel. When vectors are parallel, dot product is measured by simply their numbers. Each vector is a number, a set of number at the best. Now, these are the dot product in this case is simply their product, the product you are familiar with. But when you take these two vectors, this their dot product decreases. When you take this, it's further decrease, and when you take this, it is zero. We say the dot product a dot b is equal to zero. What about these cases? We don't need them till now. They are not needed, and when we need them, I will tell you more about this. But this is enough for us now. Till that time, dot product a we denote it by a dot b, and write a dot b is equal to ab. It's ab here. Simply, this means that if you have two vectors, their dot product is simply their product. Dot product is product, provided the vectors are fully parallel. Dot product is zero, provided vectors are perpendicular. So you can understand now what dot product is. I hope. Now suppose you have to calculate dot product of two vectors. Suppose one vector is this, say 1 2 1 2 6. This is one vector. It has three components. This x component, this is y component, this is z component. Components of a vector are always perpendicular. So components of a vector are always perpendicular. Okay, now these components which are parallel, they say these are perpendicular. Please remember one thing that I did not actually emphasize there. That is, components of a vector are always perpendicular. See, these are the two components of a vector. They are perpendicular. They are perpendicular. They are perpendicular. See, here you had components of a vector. These two, they are perpendicular to each other. They are perpendicular. So remember this thing. Components of a vector are always perpendicular. So this x component, this y component, this z component, they are always perpendicular. This is a vector. Then this is b vector. Say suppose we have another vector, that is b, column vector. We have, for example, 3 5 3 5 4, say 4, something like this. We have two vectors. Why they are two vectors? As you know from your previous lecture, you saw that an arrangement of numbers along one dimension is called a vector. So these are two vectors. Vectors are represented by columns. They are arranged. They are represented as column vectors. Column. Okay. Now, suppose we want to find this dot product. We want dot product of them. So we write a dot b, and we write then a 1 2 6 dot b 3 4 5 3 5 4. What do we do in dot product? What do we do? What I'm going to do, please look at that. The first vector is converted into its transpose. This is a column vector. When you make a transpose vector from it, that means A is to be converted into AT, and B is kept as such. ATB. That means A dot B is calculated as ATB. I will explain this why it is so. AT is transpose of this. Transpose of this is 1 2 6. And then you have B is 3 5 4. Now what you have to do, you have to take dot product. When you take dot product, you have to in dot product you will first take this and then multiply this by this. Then you will take this, multiply this by this. Then you will take this, multiply this by this. Similarly, when you take this, multiply this by 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 this, this is how you carry out this. For example, you carry out this multiplication in your school days. You used to write 2x plus 3y multiplied by 4x plus 5y, then you would do something like this. You would take up this first, multiply this by this, multiply this by this, then you would go for this, multiply this by this, multiply this by this. Something similar is done here, but here it is very simple. It is very simple. Why? Cross terms, they cancel out. Cross terms means first term of this and second term of this. See, this is first term of this, second term of this, third term of this, and for this vector, this first term, second term, third term. If you multiply first term with the second term, they cancel out. Why should they cancel out? Because see, this is x component, this y component, this z component of A. This is x component of B, y component of B, z component of B. Components are perpendicular. This is x component, this is y component. This x component will be perpendicular to y component of this, and two dot product of two perpendicular components is 0, as you can see from this. Dot product of two perpendicular components, perpendicular vectors is 0, is 0. So this dot product will come out to be 0. The product of this and this will come out to be 0. Similarly, product of this and this will come out to be 0 because they are perpendicular. But product of this and this will come out to be non-zero. That will be product of this and this will be simply, you can see, it will be simply 1 into 3, 1 into 3. Okay, 1 into 3. So it is quite nice. You have to multiply first with first, second with second, third with third. No cross multiplication, no crossing, no cross terms. There cannot be cross terms at all. So second term is 2 into 5, 2 into 5, 2 into 5. This is product 1 into 3, product 2 into 5, product 6 into 4, and you have to take sum of those products. Sum of those products, that is 6 into 4 lastly. This is all about this dot product. Now just a minute. You have this. Now I will simply show you here. This is the, I am collecting dot product here. How do I collect dot product? How do I collect it? You can better appreciate, better see it like this. This is what we get. See, 1 into 3, 1 into 3 plus 1 into 3, this into this, this into this, this into this, and we add up them. The products have to be added up then. That will give you total dot product of these two vectors. Otherwise, if you write only 1 into 3, that means only partial dot product. This is dot product of only x vectors. This will be dot product of y vectors. This will dot of z vectors. For the total dot product, you have to add them. 1 plus 1 into 3, 2 into 5, and then 6 into 4. This must be, as you can see, this is actually much simpler than this product. Much simpler than this. So you have, now this is all about dot product. Now see, what did we get? What did we get? Let us see. This is what we got. 3 ones are 3, 3 plus 2 5s are 10 plus 6 4s are 24. So we got 3 plus 10 plus 24, that is 34, a scalar. So dot product of a vector of two vectors is a scalar. Here is that scalar. A scalar, as you remember from the last lecture, is a single number. That is a single number. So that finishes the dot product. Once again, I repeat that in dot product, what we do, we multiply two components of the same type. Never multiply components of the opposite type, different type, because that will yield 0. After multiplying these components of the same type, we collect these products. We collect the products and then add them, and that is the dot product. is a measure of their parallelism, to how much parallel they are. If dot, suppose sometimes say you get a dot product value of 0, this means that the vectors are not parallel at all, they're perpendicular. So to end this lecture about dot product, we find is yes, there are a couple of questions here. Number one is, if you take dot product of these two, and by dot product we mean 1 into 3, 2 into 5, 6 into 4, why don't we take it here like this? 1 into 3, we could have done that. Why did we change this into transpose vector and then this as column vector? Why? Because the reason is that if we adopt this technique, then we can define multiplication of matrices as simply as like dot product of this definition of dot product of two vectors. That means when we multiply two matrices, we need not learn anything new. This will be applicable to that. If you do not use this method, then you won't be able to. You will have to learn something new when we go for multiplication of matrices. That is the reason, and that you will, of course, I'm not going to show you right here, because that we will do at its right time. We're going towards that as well, and I don't want to ask you to learn everything at one time. Now, one more thing, there's another genuine question is, you could have told me, sir, wanna do this thing, if you are bent upon this, wanna do this thing, keep this column vector and make this row vector. Why not this? Again, that will often violate matrix multiplication. That will go against matrix. And there is one more thing, that is, if you multiply like this, row by column, this is called inner product or dot product or inner product. If you do the reverse, column by row, then you create something new, different and new, that is called exterior product, a different thing. We don't need that right now. It is not needed. When needed, we will of course go for that now, but not at this time. So we remember one thing, that is dot. We remember a couple of things. Number one is, dot product of two vectors is a measure of their parallelism. Number one, this is one. Number two, dot product of two vectors is taken as this is taken in row. Sorry, just a minute. First I will delete this, then I will go for pen again, and then see A dot B is written as A transpose B. That is A transpose B. This is transposed. That means it is converted into a row vector. Once it is a row vector, suppose its components are A1. First X component is A1, Y component is A2, Z component is A3. These are its components of this A1, A2, A3. Then you have components of this B1, B2, B3. Then you can do it. So dot product will mean A1, B1, A1, B1, A1, B1, A2, B2 plus A2, B2 plus A3, B3. If you have an equation or an expression of this type, you can write this expression in a compact form by this, using this. As someone has said, I don't remember who said this, every equation is a story. So every equation is really a story. Now, this is about dot product. Now, in our next video, which is already there, available there, you are going to learn something. Please watch that video. Unfortunately, that video carries a tag of this math 1, machine learning math 1, but that is actually math 3. That should be math 3, machine learning math 3. Hope that you enjoy these. If you have difficulty, even as simple a difficulty as, for example, if you are not able to understand what 3x means, this 3 and x mean. Don't feel shy. Please ask me. You can do that by asking me to explain this in the group, or you can then send me a message on my personal number, and I will be more than happy in explaining this what such things mean. Remember that these lectures have been prepared or are being prepared keeping this thing in view, that our target audience is an audience that does not have any mathematical background. Thank you so much.